Alright, so today we're going to be going over a really important concept, a cornerstone concept in chemistry, and that's going to be the concept of ionic and covalent compounds. And today, specifically, we're going to be looking at the classification of these into one or the other, the properties of these different compounds and these bond types, and then the structures of them. The first thing that we're going to look at here is the classification of bonds, atomic bonds between atoms, into ionic or covalent. Now, the most important thing to understand here, the most important part is what's in red here in this red box, is that the differences between two atoms' electronegativities determines the bond type, as we can see laid out here in this handy chart. Now, in middle school, it's very likely, if you took a chemistry in middle school, you're told that ionic bonds are between a metal and a nonmetal on the periodic table, and then covalent bonds are between two nonmetals. And that's true, that's usually going to be true, but it's not because of an element's arbitrary classification as a metal or a nonmetal or a metalloid or whatever it might be. It's because those elements have properties and electronegativity values, of course measured on the Pauling scale here, that reflect the classifications of ionic and covalent. Now, looking at the properties of these two, we'll start with ionic. So ionic, of course, usually between metal and a nonmetal, but again, that's because metals and nonmetals have a difference in electronegativity that's in this range at the top here. And of course, it's going to be a bond between atoms, between ions that become atoms. One atom is going to lose an electron in its outermost shell, in the valence shell, and become a cation with a positive charge, and the other atom is going to gain that electron that the first one gave up to become an anion with a negative charge. And we'll get to that more in a second. And because of this high electronegativity value here, we're going to see that ionic compounds generally have really high melting points and really high boiling points because there's this high electronegativity difference here. It's going to take a lot of energy to pull those things apart. They're going to form crystal lattices with the ions, and importantly, these crystal lattices on their own, without being dissolved in anything, are not going to conduct electricity because the ions, they've exchanged electrons here, or rather one's given one up, one's taken another one. Those electrons aren't free to move around, so electricity can't move. If electricity is just the movement of electrons around, then these lattices, when everything's locked in place, formed by ionic compounds, are not going to be something that conducts electricity. On the flip side then, when this is aqueous, when ionic compounds are aqueous, and this just means dissolved in water as a solution, it does conduct electricity, and that's because, again, the electrons are free to move, the ions are free to move around, so electricity is going to be able to flow there. Now, on the other side of things, we have covalent bonds and covalent compounds. These are, again, going to be between two nonmetals usually, but that's because of this up here, this red box. Really important to understand that it's not just because it's between metal and nonmetal or two nonmetals, it's because of this electronegativity difference here. And with covalent bonds, as we can also see in the chart up here, there's two different types. There's polar and nonpolar, and we'll get to those more in a little bit. But in a covalent bond, two atoms are going to share electrons in their valence shell. And essentially what that's going to mean is both electrons are going to want, or both atoms are going to want to do something with their electrons. The other one maybe doesn't want it, one atom does want it, so they're going to share them, and it's going to act as it's going to act in both of their valence shells, and it's going to satisfy both of them, so they're going to work in harmony there, the overall lowering in electric potential energy. And because the lattice, it's not as rigid as a lattice up here with the ionic bonds, covalent bonds are not going to have very high melting points. They're going to have pretty low melting points and low boiling points. And they're going to have some electrical conductivity, because remember, the electron maybe is shared between two atoms here. The electron is in between these two. It's like a Venn diagram situation here where the electron is in the middle between the two. So that electron can move some, so electrical conductivity is there on a variable level, meaning that because this electronegativity difference can vary, there's quite a bit of range there between 0.3 and 1.7. It's going to vary. The higher it is, it's going to be lower conductivity. The lower it is, it's going to be able to move around more. And that's going to be more conductivity. And of course, solubility is the same way. That's more chalked up to intermolecular forces, which is not a topic we're covering today, but covalent bonds will have variable solubility in water. So now we're going to be looking at ionic bonds specifically and their structure. And I've kept our handy chart up here to make sure we understand why ionic bonds are the way they are. And of course the same definition here. It's a bond between ions. Atoms will ionize themselves, or get ionized rather. They'll exchange that electron, they'll form a compound. So we talked about cations and anions. Cations are the atom that loses the electron in its valence shell to become an ion, and it's going to have a positive charge. So cations are positive. Anions then are negative, and they are the ion that gains that electron in its valence shell. So think of it this way. If we have a sodium atom and a chlorine atom, sodium atom has one valence electron in its shell. The chlorine atom has 7. 1, 2, 3, 4, 5, 6, 7. This sodium atom really wants to get rid of this electron here. This chlorine atom really wants to gain this electron here. So this atom, right now, the sodium has a positive charge. Chlorine atom has a negative charge. So what are we going to do with this? So what's going to happen is sodium is going to give this electron to the chlorine, and it's going to bond like this. So chlorine now has a full outer shell, a full octet here is what it's called, and then sodium also, it doesn't have that, but it's bonded to the chlorine here. That's what happens when we get something like this. And another example, say we have a lead 2+ here. We're not going to draw the structure here just to get the idea, but this lead is a 2+ ion. It's a cation because it has a positive charge and it's got a 2+ charge, meaning it lost 2 electrons. Chlorine here is going to have a single minus charge. Now, since there's 2, if we want to make a compound here, we have to do 2 chlorines, but this is going to form lead 2 chloride. And that's because the lead ion, is going to give its electrons over here. And when that happens, this is going to form as a result. Okay, so now we're going to be looking at the other side of things. We did ionic, now we're going to look at covalent bonds. Now remember, covalent bonds, they're going to form covalent compounds, which are called molecules. Ionic bonds are, of course, called formula units. Covalent bonds are called molecules. And remember, here's our chart. We have our covalents down here. Polar and nonpolar. And that's just going to mean the electronegativity difference is going to reflect a bond between 2 nonmetal elements. And remember, we discussed that covalent bonds, generally, they're going to share, or they are going to share an electron. So if we have sort of a Venn diagram here, the outer shells of electrons, here's atom A, here's atom B. This electron is going to be shared between the 2. And sometimes what's going to happen is you're going to have one atom that's going to want to bond with other atoms, and you're going to get an expanded octet. And we'll see an example of that here in a second. But all that means is that the central atom of whatever it is it's bonding is going to have more electrons than just the 8 in its outermost shell and its valence shell, and it's going to look a little bit funny. It's going to have a little bit different geometry. We're going to discuss geometry here in a little bit, but just know that that's a thing that can happen and be ready to see it. It's nothing weird, nothing normal. If you see that in a problem and you're thinking you may be messed up, you probably did it right, because that's a unique property that some compounds can have. And the 2 core types of covalent bonds, well, the 2 types at all, are nonpolar covalent and polar covalent. And nonpolar covalent is when we have a distribution, a charge distribution that is relatively symmetrical. It means the electrons are relatively the same. It's not being pulled one way or another more toward either atom. And that's down here. That's going to be when maybe like O2 is going to be considered a covalent, a nonpolar covalent bond, because it's 2 of the same element, same electronegativity. That electron isn't going to be pulled toward one or the other more. Now, some bonds are going to be different elements, but they're still going to have this lower electronegativity. Now, an important thing to note about nonpolar covalent, even though our chart up here says nonpolar is only up to 0.3, a carbon-hydrogen bond is considered nonpolar covalent, just because it's so prevalent, especially in organic chem. So remember this. This is important to understand. Even though our chart says this up here, this is important to have like as a reference here. And then on the other side, polar covalent is not nonpolar, and that's going to mean that the electron is going to be pulled more toward one atom than the other. And it's going to have a little bit higher of a difference in electronegativity here. It's the most variance on this whole spectrum. And this is going to lead to atoms having a partial positive and a partial negative charge. Now, when we look at this, we indicate that with a delta. It's a Greek character. Delta looks a little bit like a music note. We're just going to indicate a partial positive with this here, and then a partial negative with this here, with a negative and a positive superscript above it for polar whenever we need to. And on the topic of polar covalent bonds, they're going to have unique something called polarity, and that's just going to represent the dipole moment of the molecule. And again, asymmetrical charge distribution. We indicate this with an arrow, so if we have maybe molecule A up here is more negative, molecules B or atoms B and C down here are more positive. You can't say that's a whole negative because it is covalent. Maybe this one is more electronegative. So this is going to be a delta minus, and this is going to be a delta plus down here because the atom A is going to be more electronegative than its friends over here. So we'll erase this here just so we have a little bit more room if it wants to erase. That's good enough for now. And so this atom is going to pull electrons more toward it than these two. So when we draw our dipole arrow, it's going to look like this, an arrow pointing upwards toward the more negative end, and this cross, this perpendicular line here. It looks a little bit like a plus sign. That's how I remember it down here with the more positive parts. And then I'm going to erase some of this now. We're going to get to Lewis structures, and Lewis structures are a handy way to represent ionic compounds, or sorry, covalent compounds, molecules. And we do this by summing up all of the valence electrons that each atom has, Lewis structures down here. And we draw a little picture to understand where the bonds are and what it's going to look like. It doesn't reflect accurate 3D geometry, which again we'll talk about in a second, but Lewis structures are a handy way to just show like a little footnote of what the molecule looks like if you were to draw it out and look at it. Okay, so we're going to do some practice. We're going to learn how to draw Lewis structures here. We got 3 examples and 3 more on the next slide. So Lewis structures deal with the valence electrons in a molecule, a covalently bonded group of atoms. So the first thing we want to do when we have a Lewis structure and we want to draw something, a Lewis structure, is we want to count up and add together the number of valence electrons, the total number of valence electrons in the molecule. So atom A's valence electrons plus atom B's valence electrons, so on and so on. So for CH4 here, methane is our first example. We're going to count the valence electrons for carbon, and we're going to count the valence electrons for hydrogen and multiply that by 4 because there's 4. So carbon has 4 valence electrons. Hydrogen only has 1. It's in the first thing. It's the first element on the periodic table. You know, it's only got 1 valence electron. But because there's 4 of them, we're going to multiply that by 4. So 1 times 4. That's going to be 4 plus 4, and 4 plus 4 is in fact 8. So we have 8 valence electrons here in our Lewis structure that we need to use. Now the second thing we need to do in a Lewis structure is pick a center atom we want to use. Now for our purposes, we're not going to be going into anything about why something makes a good center atom, so we're just going to be looking at what atom does things branch off of. So we have 4 hydrogens and 1 carbon, so the center atom must be carbon. And carbon in general is going to make a really good center atom. It's really common to see carbon as a center atom. It wants to make 4 bonds. So we're going to go ahead and draw our center atom here and draw our hydrogens. We have 4 of them around it. 1, 2, 3, 4. Now remember, each atom, and well, not each atom, most atoms in most contexts are going to want to have a full outer shell, a full octet. Octet, what's that sound like? That's going to be octo, 8. So a full outer shell means, a full octet means 8 valence electrons around this atom. So we have to figure out how to use these, and this is convenient because there's 8 valence electrons here we want to use. So we need to figure out where to put these electrons in this molecule to make it work. And remember, because this is covalent, things are shared. So if we put our electrons in our diagram here, we're going to have 1, 2, 3, 4, 5, 6, 7, and 8. So we've used all of our valence electrons here, and that's good. Whenever you have a Lewis structure, you always you have to use all of your valence electrons that you've counted up. You can never add any more. You only have what you're given from the compound, and you must fit those into your structure. And again, remember, because this is a covalent compound, these electrons are shared. And we can denote that in a Lewis structure by using a line instead of two dots. So we can go bup, 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 bup. Each line is going to represent 2 valence electrons. And because we have 4 lines, there's 8 valence electrons total. So this is our correct Lewis structure for methane, CH4. That is how our Lewis structure for methane looks right there. So I'm going to go ahead and erase this and go ahead and move on to our next example. Our next example is H2O, water. We all know it, we all love it. Water, what's the first thing we need to do when we have a Lewis structure? Remember, we have to find the total amount of valence electrons. So if I write my little sigma here, valence electrons equals hydrogen. How many valence electrons does hydrogen have? If we look at the periodic table, we see hydrogen has 1 valence electron. But because it's a subscript 2 here, we multiply that by 2. So 1 times 2 plus, that's our hydrogen taken care of. Oxygen, if we look at the periodic table, has 6 valence electrons. So if we sum these together, 1 times 2 is 2, plus 6 is 8 valence electrons. And this E sub superscript minus is just slang for an electron. So let's go ahead and pick our center atom now that we have our total number of valence electrons figured out here. The center atom here, what branches off of? What atom does thing branch off of? If we look at this, there's 2 hydrogen and 1 oxygen. So in our structure, we're going to pick oxygen as our center atom. So let's go ahead and draw our atoms out. Oxygen, put hydrogen 1 over here, hydrogen 2 over here. And remember, we want our center atom to have a full outer shell. So we're just going to put these 2 here, bum, 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 bum. And remember, because this is a Lewis structure, instead of doing 2 dots, we can just draw 2 lines here. This is the same as 2 to share. It's the same as a electron pair, a shared pair there. But that's only 4. We have 2 valence electrons left. We know that we need to put them somewhere with oxygen because oxygen only has 4 electrons in its outermost shell. We want it to have 8 for its full octet. But we can't put them here. We can't do this because even though oxygen would be happy with this, hydrogen would not. Hydrogen, we don't need to put anything else other than a single line extending to it. Let's fix that. We only need a single line in hydrogen because we only want it to have that many electrons in its outermost shell. So in an instance like this, we just stick the extra electrons around the center atom like this. And this way, oxygen is happy because it has 2, 4, 5, 6, 7, 8 electrons in its outermost shell. Hydrogen has just this line connecting it. So this is our correct Lewis structure for water, H2O. And if we were to draw our partial negatives and our partial positives here, actually let's draw it a little bit differently. Because we know that like charges repel, we'll get to this more in a second. Our more geometrically correct model would be this way. H, H, and then our 2 lone pairs up here. If we were to draw our dipole arrow, it would look something like this. It's more positive down here. Oxygen is more electronegative, and so it's going to have a delta minus. Well, these hydrogens down here are going to be less electronegative, have their electrons poured more toward the oxygen, going to be a delta positive. And this is our Lewis structure here. This is a demonstration of polarity right here. So both of these are correct. They both mean the same thing. This is just a Lewis structure. This is a Lewis structure plus polarity indication here. It's the same thing. Both are correct here. So I'm going to go ahead and erase this, and we're going to move on to our final example. Now look at this thing over here. Our final example is SF6, sulfur hexafluoride. That's a big element name, right? So remember, it may look big and we've not done something with 6 other atoms attached to a single one, so we'll just do it the same way, follow the order, you're going to be okay. So the first thing we do whenever we see a Lewis structure we want to draw, sum up the number of valence electrons. So number of valence electrons. If we look at our periodic table, we see sulfur has 6 valence electrons. That's going to be 6 plus, and if we look at the periodic table, we see fluorine has 7 valence electrons. It's one away from making that full outer shell. But because there's 6, a whole 6 fluorine, that's going to be 7 times 6. And if we do this, we can use a calculator if we need to. 6 plus 7 times 6 is going to be 48 valence electrons. Wow, look at that. 48 valence electrons we need to use in our structure. And what's the second thing we do whenever we have a Lewis structure? We want to figure out which atom we want to make our center atom. So this one, we're going to choose sulfur because there's fluorines, there's 6 of them, there's only 1 sulfur. So sulfur has to be our center atom. So I go over here and make my sulfur in the middle. That's not an S, here's an S. And I put my 6 fluorines around it in a pattern that makes sense. Or really any pattern. A Lewis structure doesn't have to be geometrically correct. We just see that there's 6 fluorines around this. Now obviously we know that this is going to be bonded. The sulfur is going to bond to all of these because it is a single compound here. We can draw our lines to these fluorines. So 2, 4, 6, 8, 10, 12. So we've 12 of our 48 electrons. Now the rest of them, where do we put them? We have to put them around fluorine. Fluorine is not like hydrogen. It's like almost all other elements where you have to give it a full outer shell for it to be happy here. So we have 2, 4, 6, 8, 10, 12. So the rest of these electrons we're going to assume go around fluorine. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and 48. And this is our completed Lewis structure for SF6. Sulfur hexafluoride. This is what it would look like if we find a Lewis structure in a dictionary. This is what it looks like. And all we did here is take the valence electrons that we calculated, we put it around a center atom, and we stuck the dots in there to make things work. Now, remember on the last slide when I talked about expanded octets? This is an example of an expanded octet Lewis structure. Because normally, sulfur only wants to have 2 bonds. Sulfur usually only wants to have something like this, where it is bonded to 2 atoms over here, whatever that may be. That's not what happened here. Sulfur bonded with fluorine 6 times, 6 fluorines. It expanded its outermost shell to bond with 6 fluorine atoms, and it works because it's still stable. And so this is an expanded octet example. Sulfur hexafluoride SF6 will look like this. Remember, it's normal to see something like this. As long as it works up here, you've most likely done it correctly. Alright, so we're going to do our last 3 examples for practice drawing Lewis structures. Just like everything else, we're going to follow the same order of steps, and we're going to be okay doing this. So before anything else, the first thing we do with any Lewis structure is sum up the number of valence electrons. So phosphorus, if we look at the periodic table, has 5 valence electrons. Fluorine, we know from the last example, has 7. Because there's 5 fluorines in the compound, there's going to be multiplied by 5 there. If we do this in our calculator, we're going to see it's 40 valence electrons here. So we pick our center atom. Our center atom is going to be phosphorus because there's 5 fluorines and 1 phosphorus. Phosphorus must be in the center. Let's go ahead and draw this out then. So phosphorus there, fluorines. Let's draw our fluorines around the phosphorus. There's 5 of them. We just draw there. We know the phosphorus bonds to all of these, so we'll draw lines. It's a bit further away than the rest of them visually, but it's the same. So 2, 4, 6, 8, 10. Just like the last example, we have to fill in fluorine's outer shell for it to be happy. So we have 10 so far. Let's fill the rest of these. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. And this, let me fill in the dots to make them not so faint, is our completed and correct Lewis structure for phosphorus pentafluoride. Now, what's another thing funny we notice about this? Just like our last example, this is in fact an expanded octet Lewis structure, because instead of just having a lone pair here, phosphorus decided to have a whole other bond with this other fluorine atom over here. So instead of there just being this lone pair here, which there's not in this molecule, there's a whole other bond. Phosphorus usually wants to make 3 bonds, but instead it made 5. So this is classifiable as an expanded octet. Remember, that's a normal thing to see. If you see it, it just means, especially molecules like this, you did it right. So we're going to go ahead and erase this as our Lewis structure, move on to our next example. And our next example is NH3, which is ammonia. So just like anything else, we're going to go ahead and sum up our valence electrons. Sum of valence electrons. If we look at our periodic table, we see that just like phosphorus, ammonia has 5 of them. Hydrogen, being the first element, only has 1 valence electron. It's its only electron. Because there's 3, we're going to multiply that by 3. 1 times 3. It's going to be 8 valence electrons. So let's pick our center atom like always. Nitrogen we're going to pick as our center atom. Nitrogen. We're going to draw our hydrogens around it. 1, 2, 3. We're going to connect our bonds 2, 4, 6, and because we do have a 2 electron deficit here, we're just going to stick them here along this nitrogen as a lone pair. So let's make this a little bit more pretty. So there's 2, 4, 6 there, and then these extra 2 right here. And this is our Lewis structure for ammonia NH3. This is not an expanded octet. This is just like how it should be. Just a quote-unquote normal ammonia, normal nitrogen octet here. Except we don't have a 4th hydrogen, so we don't put a 4th there. We just put this 2 electrons here as a lone pair. This is our Lewis structure. So I'm going to go ahead and erase this. We're going to move on to our last example, which is pretty unique. It's not like any of the other ones we've seen today, I don't think, because it's got a unique property. We'll see when we get to it. So carbon dioxide, CO2, we should all know about this one. Why not draw a Lewis structure about it? So the first thing we do, like always, we find our number of valence electrons. Carbon we know has 4, oxygen we know has 6. We're going to multiply that by 2 because there's 2 oxygens. 12 plus 4 equals 16, so there's going to be 16 valence electrons here. We'll pick our center atom. Whenever we have carbon, it's usually going to be carbon as our center atom, so we're going to pick carbon here. So I'm going to draw this over here to the side a little bit because there's a unique property I want to point out about this one and other compounds. So carbon is our center atom. We're going to put our oxygens to the side. We're going to fill in our bonds. Carbon wants to make 4. Oxygen wants a full outer shell, so we'll do this. Bum, 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 bum. And this is a correct Lewis structure. There's 2, 4, 6, 8, 10, 12, 14, 16 electrons. Carbon has 4 bonds, it's happy. Oxygen, each one has 2 bonds, it's happy. So this is good. And so I'm going to draw brackets around this one. I'm going to point something out here. Why can't we draw it like this? We have carbon has 4 bonds. Oxygen, one of these has 3 bonds. Why can't we draw it like this? Well, the answer is we can. This is called a resonance structure. When we have a molecule whose Lewis structure can be drawn multiple ways, and one is not more correct than the other, we call that a resonance structure. By logic, the other resonance structure is just a mirror flip of this one. It's just going to be the oxygen with 1 bond over here, carbon here, triple bond to another oxygen with 1 pair there. These are all the same molecule. These are all CO2. All 3 of these are. And we call these resonance structures. And let's explain why these work for a second. So in an ionic compound, this is not possible because ions are locked together. We have lithium chloride here. These ions are locked together. They want to be with each other and they form a lattice. Their electrons are not free to move. In a covalent compound like this, these electrons, they're not locked in one place or another, so they can move around. Electrons are never still. In fact, they're chugging around at or near the speed of light in these molecules here. So at some point or another, giving the probability of the electron region, an electron that's being shared here will end up over here at one point. And this is going to be the structure. That same electron or any other electron is going to be over here at some point in this bond instead of being over here like it was. And because electrons aren't still, all 3 of these can be true at the same time for a given molecule or at different times for a given molecule. Group of molecules, resonance structures are a very real thing, and scientists verified that the actual Lewis structure for carbon dioxide and any other molecule that has a resonance structures like this is an average of the 2. So really, the Lewis structure for carbon dioxide is going to be an average of all of these three Lewis structures down here. And while all three of these are correct, I'm going to go ahead and draw a circle around this one because this represents the average. This bar here means average of the Lewis structures between these three. And again, we just denote Lewis structures with brackets and arrows between them. If this was a polyatomic ion, we just put the charge here, whatever it might be, but because it's a neutral ion, it's just carbon dioxide, this is all we have to do here. So now we're going to move on to molecular geometries, and I've referenced a couple different times now, a couple different instances. Well, this is not maybe the most geometric correct model, or the geometry of this might look a little bit different, so we're going to be going over that right now. So the leading and most experimentally verified model for molecular geometries is called VESPER, or I pronounce it VESPER. It stands for valence, shell, electron, pair, repulsion. And then there's a theory at the end. Theory just means it's something that's been put forward and it's been experimentally verified, so we know it's a good thing. So essentially what this idea is going to do is, given the number of total electron regions, here I'll circle these here, and then the number of bonding and non-bonding regions, or domains, you'll sometimes hear them called, all these numbers, you can determine the shape of the molecule and the geometry of the molecule, along with the approximate bond angle between things. This is 180, 120, less than 120. And in addition to that, you can also deal with hybridized orbitals. Now, this is a handy chart here that's excellent reference. It's got some pictures, it's got an excellent layout of what's going on, you know. It does list hybridized orbitals as well. Hybridized orbitals are not something we're going to be talking about in this video. They're a little bit more complex, but just know that when covalent bond happens, the valence shells of the two atoms, they can't both stay the same, so they compromise and they hybridize. And that's what these are. So we'll walk through this. If there are two electron regions, and electron regions, we should probably clarify, electron region or domain, sometimes you hear it called, along any atom is going to be just the area that's being bonded. So in this molecule there are 2, in this molecule there are 3, here there are 4, and this was that notation I did earlier where I did the dashes here and then the thicker one. This is what I was getting at, this structure here. Same thing over here, this has 6, this has 5. We actually drew the Lewis structures for these right here that I've just circled right now. We did the Lewis structures for those a bit ago. But it takes the total number of electron regions here and it categorizes them into which ones are bonding and which ones are not bonding. And the bonding ones, of course, just mean, is there another element there that's participating in bonding? The non-bonding regions are something where there are electrons there, but they're a lone pair, like this one. This trigonal planar one has 2 bonding regions, of course, but it has 1 non-bonding region. So it's got these two atoms right here that it's bonded to. It has this lone pair along the central atom, and with that we can see that there's bond angles. So why is this necessary? We should probably address that. This is necessary because if we draw methane as CH4 like this, well, this is in 2-dimensional space, right? If electrons don't want to be close to each other, per Coulomb's law, like charges repel. So these electrons, if they can get further than 90 degrees apart, they will. And this is in 2-dimensional space. In 3-dimensional space, we're going to see this tetrahedral one right here. This is what we're going to see in 3-dimensional space for methane, CH4. So we're going to see that one hydrogen's obviously going to go straight up, one's going to go down in one direction, one is going to come towards you, and that's what this darker one here is for. And then one of these hydrogens is going to go off away from you. And we're going to see that the angle between these hydrogens is about 109.5 degrees there. Now when there's a lone pair here, or any lone pair here, just like here, we're going to see that that angle is going to be decreasing a little bit because, as it turns out, a lone pair of electrons is going to push away a little bit more than an entire bond. So if I was going to eraser mode here, get rid of this for a second and I draw a lone pair here instead, this angle is going to become a little bit less than 109.5 because it's going to push these atoms down here away from it a little bit more. And that's a really unique thing here. So this is called Vesper theory. This is an excellent thing to memorize, especially this first page right here. Memorize it if you haven't already. Take a picture of it, whatever, really important. This is also important. This is our expanded octets page. There are way more than these, I'm sure. Well, I know that there are more of these, but on here there are more combinations than just 5 and 6 bonding regions, of course. But these aren't as important to know as these if you can understand that there is a number of bonding regions that can be categorized into non-bonding and bonding. And from that you can deduce a shape right here and then a corresponding geometry for the shape. So this is going to be the shape in this first column here. The geometries possible for that shape are going to be right here. If you can memorize these, you'll be all set. So we're going to be doing some practice problems with these in just a second. Remember that bonding region is the same thing as an electron domain, and that these are modular. So if we have an example where we're going, like there's multiple carbons, or if we draw, we're going to draw the Lewis structure for this in a bit, but if we have this, each one of these carbons is going to have one of these geometries. It's going to turn out to be tetrahedral here, but this doesn't just apply to molecules that are tetrahedral in this fashion. Of course, this is tetrahedral. It doesn't just apply to things like NH3, ammonia. You can do long chains of molecules here that behave like this, and you can describe it with the same thing. It's very modular. But this is really important to understand the geometry. It's going to have a lot of effect on the properties of that molecule, as it turns out, and this is why. It's because the valence shell electrons are going to repel each other, and it's going to create geometries with specific bond angles just like this. Alright, so we're doing our last thing before our practice and review problems today, and that's going to be the effects of electromagnetic radiation in molecules. So we've got some points here we're going to go ahead and read. It says electromagnetic radiation is made up of photons traveling at different wavelengths along this spectrum here, which is the electromagnetic spectrum. We'll draw an arrow down here. And we can look at some properties here. So as wavelength is going to decrease, energy is going to increase. So as wavelength, we'll call that lambda, is going to go down, energy is going to go up. These are in correspondence to each other. And of course, short wavelength, high energy, long wavelength, low energy. We can only see a small part of the spectrum here. That's right here. Low frequency with long wavelength, high frequency with low wavelength. That all makes sense with our intuition. So we're going to go back to our second point up here. It says all light, including visible light, which is this tiny area that we can see, this tiny area of photons that we can pick up in our eyes, is going to be this visible light here, this whole rainbow of colors. Corresponds to a specific wavelength of electromagnetic radiation. And actually, as a cool little fact here, magenta would be somewhere over here. It's not a real color. Our brain does something funny, and magenta is actually over here, the wavelength that our brain interprets it to be. But that's neither here nor there. Back to the point, different wavelengths of electromagnetic radiation are associated with distinct intermolecular effects. So, and these three are listed right here. So the first two are pretty similar. So infrared radiation, infrared light, this area right here, is going to be associated with vibration and stretching inside of the molecule. Microwave radiation, so this area right here, is going to be associated with molecular rotation. So you get some rotation going on whenever you give it microwave light, microwave radiation. And then visible light, visible radiation is a special one because this is talking about the photoelectric effect, or it's something, it references something that the photoelectric effect proved. Photoelectric effect. And that was something that Einstein did to show that electronic transitions do happen. Electrons are ejected when certain wavelengths of light are shown, and I believe it was a metal he did. This also talks about the excitement and release of light in atoms when you feed it energy. So when you give electrons an atom, why don't we just draw like a fictitious element here? When you give, and we'll do circles up here. When you give this atom, so electrons, some energy, let's say the electron starts, let's make this a bit bigger, let's say the electron starts somewhere down here. Let's say this is where the electron starts. When you give it some energy, that electron is going to jump up here. That energy is going to be in the form of a photon along the spectrum. It's going to be in the visible light region. When you give some energy, that electron is going to go up here. And then because that energy has to be conserved, eventually the electron is going to go and settle back down here. And that's when you release more photons that you can see. That's going to be the visible light that we can't see. And that's exactly how most lights work. You give energy to atoms, you excite them to go up from their ground state, and they release that energy when they go back down, and that's our visible light. Visible light. And on the topic of visible light, the things that in a molecule that interact and absorb that visible light are going to be called chromophores. Because we are talking about molecules here, that's a cool little term to know. And that is our slide here, so we're going to go on to move on to our review next. Alright, so we've reached our second to last slide. Now we're going to start our review with 3 practice problems here, just to make sure we understand and go over the material that we talked about today. So the directions read, for each given compound, determine if it's a molecule or a formula unit. If it's a formula unit, you're going to draw a structural representation, including charges and indications of cations and anions. If it's a molecule, you're going to draw a Lewis structure. And if it's not an expanded octet, you're going to additionally include molecular shape, geometry, and bond angles for each atom in the molecule. If it's polar covalent, you're going to determine the polarity and indicate the dipole moment visually. And you're also going to include partial charges here. So we're going to work through these 3 and follow these directions. So our first example here is xenon hexaiodide. First part of the question asks, determine if it's a molecule or a formula unit. Well, is this, that's easy. Is this polar? Is it some sort of covalent? Is it nonpolar, polar, some sort of covalent, or is it ionic? Well, the answer is it's going to be covalent. So that's going to make it a molecule. Why do we know that this is true? Because if we take the electronegativity difference between xenon and iodine, it's going to be relatively small. And that means it's going to be a molecule. Never mind, it's of course between metal, but of course between 2 metals, electronegativity difference is going to confirm that, so we know that it's a molecule. So the second part of the question is going to ask, if it's a molecule, we're going to draw this thing a Lewis structure. So the first thing we do whenever we want to draw a Lewis structure is what? Sum up the total number of valence electrons. So total number of valence electrons. Xenon is a noble gas, so it's going to have 8 valence electrons. 8 valence electrons. And then iodine is a halogen, and it's going to have 7 valence electrons. Because there's 6, it's 7 times 6. And 8 plus 7 times 6 is going to be 50 valence electrons, quite a lot. 50 valence electrons in total. And with that, we can draw our Lewis structure. So we're going to pick xenon as our center atom here, of course. We're not going to worry about formal charge here because that's not something we have to consider. So no resonance structures. But xenon in the middle here. We're going to put our iodines around that. 1, 2, 3, 4, 5, 6. Of course, make our bond. So 2, 4, 6, 8, 10, 12. Fuel the outer shell of the iodine. 1, 2, 4, 6, 8, and 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. And because we have 2 more valence electrons we need to use, we filled up all these outer shells. We're going to put these as a lone pair around xenon. And this is our Lewis structure right here. And so the last part of the question asks if it's polar covalent. We're going to determine the polarity and indicate that with a dipole moment arrow. We're going to include partial charges. So is this polar or nonpolar covalent? Well, it's going to be polar. And remember, polar is just an asymmetrical charge distribution. Whenever there is a lone pair here, it's going to be considered polar. So our dipole arrow is going to be a little bit tricky to draw on this one because there are 6 iodine atoms around it and a single lone pair. It can be tricky in 2D space, but as long as we know that there's polar, we know that in reality the arrows would all be going out like this. Xenon will be slightly more positive because iodine is a little bit more electronegative than xenon is. And with that, we can say that iodine is going to have the partial negative charge. All these iodines are going to have partial negative charges, and then xenon, they're going to have a partial positive charge because it's slightly less electronegative than iodine is. And this is our completed question for problem 1. So we're going to go ahead and erase this and move on to part 2, or rather problem 2, same question, problem 2, part 2. Now, let's go ahead and read the question again. If it's a molecule or formula unit, so what is this? If it's a molecule, it's covalent. If it's a formula unit, it's ionic. If we take the electronegativity difference between aluminum and oxygen, it's pretty easy. That's ionic. This is going to be an ionic compound. And again, of course, you can use the middle school rule. If it's a metal and a non-metal, it's ionic. So we'll say that this is ionic. That's not so faint. Ionic. Right here, ionic. So we don't need to draw a Lewis structure or anything. If it's a formula unit, draw a structural representation. So what does that mean? What do ionic compounds form? Ionic compounds form lattices between their ions. So aluminum forms a 3+ ion. In this instance, oxygen forms a 2- ion. So 6 plus -6 is 0, so this is how it is. This is why the molecule is balanced in this way. Two aluminums per 1 oxygen. Formula unit, not molecule, excuse me. So we can draw this in a lattice for a single one of these as Al3+, O2-, O2-, Al3+, and then we'll stick an O2- here. And in reality, this of course would be more. There'd be a whole lattice of these here, but this is good enough for what we're doing today. And then the last part of this says charges. We did that. Our charges are 3+ and 2- respectively. And we need to indicate cations and anions. So what do we know about cations and anions? Cations are positive. So the cation here will be the aluminum 3+. Then the anion here, let's make this a bit better. Anion here will be the O2-. This is our response to this part of the question. Now, an easy way to remember cations versus anions. I like cats a lot. Cats are positive, so cations are also positive. I'll draw a little picture here. Cat, ion is equal to positive. Cat, you draw a little face here. They're both positive. We love cats. I love cats. So this part of the question answered. Cation is the aluminum 3+, anion is the O2-. This is our lattice, our structure. It's ionic compound formula unit. So we're going to go ahead and erase this and move on to our third part of the problem here. And the first part, just like the last two times, is it a molecule or a formula unit? So remember carbon and hydrogen. So this is going to be a molecule right off the bat. We should know that by now. Molecule. So what is the electronegativity difference for carbon and hydrogen? Well, it's going to be 0.4. Technically, the cutoff for nonpolar is 0.3, but remember the little distinction between carbon and hydrogen. This is going to be considered a nonpolar bond because it's so prevalent, especially in organic chemistry and complex organic molecules. So this is going to be nonpolar. So we know it's a molecule. We don't have to do any sort of dipole moment. We do get to draw the Lewis structure though. So what's the first thing we do whenever we draw a Lewis structure? Just like last time, just like always, sum up the number of valence electrons. The sum of the number of valence electrons, carbon has 4, there's 4 carbons, so 4 times 4 plus 1 times 10 is going to be 4 times 4 plus 1 times 10. To be 26 valence electrons, so a decent amount there, 26 valence electrons. So our center atom, there are less carbons than there are hydrogens, and carbon always makes a good center atom, especially in molecules like this. So we're going to do carbon as our center atom. Because we have 4 of them, we're going to line them up like so. Carbon, 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 carbon. Space it out a little bit more. We call this a carbon chain, and let's space our hydrogens around these carbons. We have 10 hydrogens, so 1, 2, 3, 4, 5, 6, 7, 8. Now we can put 2 on the ends here as well. we have 26 electrons we need to use. So obviously, these are all connected. So we're going to give all the hydrogens to the carbon. So it's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have 6 valence electrons left. The only thing we're missing is these 6 in the middle to bond the carbons together. So it's going to be 22, 24, 26. And this is our Lewis structure for this molecule. This molecule is called butane. That's not what I want. This molecule is called butane, and it is C4H10. So what's the last part of the question? The last part of the question says we need to include the molecular shape and geometry and bond angles. So we got lucky here because all 4 of these carbons have the same shape, geometry, and bond angle. Not the same electrostatic stuff going on because some are bonded to hydrogen all the time, some are bonded to carbon another part of the time. So we've got some interesting stuff here. But as far as word is concerned, shape, geometry, bond angle, that's easy. So we'll call this carbon 1, carbon 2, carbon 3, carbon 4. So carbons 1 through 4. Let's move this up a little bit. Carbons 1 through 4. Let's make a little chart here. Carbons 1 through 4 are going to have a shape. Remember from our sheet here, the shape is going to be, and the geometry actually, is going to be tetrahedral. Tetrahedral. Remember, tetra is our prefix for 4, and hedral just means it's in 3-dimensional figure. So there's shape and geometry taken care of. Bond angles in any tetrahedral atom, any tetrahedral molecule that does not have a lone pair is going to be 109.5 degrees. So the bond angle is going to equal 109.5 degrees. And then this is our final answer for all of this question. We're just going to draw a box, maybe not include all of it, but this is our answer here. So this does a good job of combining everything that we've talked about. Here again, not polar, because carbon and hydrogen considered a nonpolar bond. So this is going to be our answer for the third part. Okay, so we've come to our last slide, the second half of our review question, and these are just 3 easy ones to make sure we understand this electromagnetic effect on molecules. So it says for each question, select the correct answer. So the first one is, what is microwave light associated with in molecules? Microwave light is going to be associated with molecular rotation inside the molecules. Second part asks, what is visible light associated with in molecules? That's going to be electronic transition, so it's not rotation. Can't be that, we already have that one selected. So this is just going to be, remember, we have our atom here, our fictitious atom. We create our fake orbitals here, and this electron is down here. Maybe it gets some visible light here. It goes up here, gets really excited, and then it realizes it has to go back down. And because energy and mass have to be conserved per a law of conservation, this released is going to be visible light. So that's going to be the electronic transition because that electron jumped up and then jumped back down. That's what that term electronic transition means. And then because for this last one we've ruled out A and C, infrared light must be associated with molecular vibration. And we should probably add molecular vibration plus stretching inside the molecule. So visible light is just this little part of the spectrum we can see. Down here expanded. Electronic transitions are associated with that. Rotation is going to be microwaves over here. And then infrared is going to be this area over here associated with vibration. And that is all for our review.